Alright, let's do some arc lengths, yeah? Polar equations, if you're not afraid. Let's do it. Forgotten to turn my backlight on. Alright. So, the problems look a little like this. Find the integral that represents the arc length for some loop, whatever. We'll try the outer loop since we already worked on this problem before. I know a couple things about the outer loop. It starts when theta is equal to 0. And it keeps tracing. When it gets to here, the theta is about 2.0 radians and some change. So it'll be easy to trace at least that half of it. Then we can always multiply by 2. That's going to help me figure out my limits because I'm using the knowledge from the previous problem. And if you didn't see it, what we did is we just set r is equal to 0, and that defines the points where it crosses the origin. And one of them was this one around 2 radians. The other point here is the starting point. When theta is equal to 0, you get 10. Any case, talk is cheap, let's do it. So what we do is we cut up into infinite many small little tiny diagonals called ds. And now on each one of them, what you would do is you would turn that into a tiny baby hypotenuse on a right triangle, and you'd make a right triangle out of that and make a little microscopic Pythagorean theorem, and that would lead you to believe that perhaps ds squared is equal to dy squared plus dx squared, or said differently, ds is equal to the square root of dy squared plus dx squared. Not bad, right? And then we've got a lot of variables here. We've got s's, x's, y's, r's, thetas. It's all over the place. So the gist of it is to try to get it all into one variable so that you can integrate. I mean, I could integrate here, and the idea sounds nice because that's really all we have to do is use the grace and power of the fundamental theorem of calculus to add up all these little areas, and then all these little segments, and then we're done. And here again is the trouble that you've got too many variables. So to do that, let's do a little bit of work before we go there so we can come back here and replace it. Recall that there's a relationship between y and r's and thetas, and it goes like this. Y is equal to r times sine theta. That would tell me that dy is equal to, I'm slapping a d on both sides, so it would be sine of theta dr plus r times cosine theta. The derivative of sine is cosine theta. And then I could even get a dy square here, and I'll do the dy square in red. Dy square, that would be equal to a sine square theta dr square plus, I gotta FOIL this, right? Squaring that side and squaring that side. So that would give me 2 times r times sine of theta times cosine theta times dr. And then I gotta do the last one, that would be r square cosine square theta. And of course there is a d theta here. That would put a d theta square there. Okay, now it's done. Because that was implicit differentiation. We slapped a d on both sides. So both of them should have d's. Alright, now what? So we have something similar for x's. I think the one for x went something like this. X is equal to r cosine theta. So therefore the differential of x would be equal to cosine theta times the differential of r plus, actually it's minus, r times sine theta d theta. That's the derivative differential of cosine theta. Sine theta, actually negative sine theta d theta. And then I need to square it so I can plug it in there. So I'll square it in red. Dx squared is equal to the first one squared. That would be cosine square theta dr square minus 2 of these guys, 2r cosine theta sine theta dr d theta. That was a d theta as well. When you minus, no, this would actually be a plus because it's squared, r square sine square theta d theta squared. It's easy as it might seem, that's all you have to do. Duh, unexpected result. I'm kidding. Then you have to add them all up. On the left hand side you have to add up the dy squared and the dx squared. Why? Because I have to add them up here so I can plug them into my ds formula. So I have that dy squared plus dx squared is equal to, I have to add these. Notice I have a sine square theta and a dr square and a cosine square and a dr square. That means I have a dr squared times the quantity sine square plus cosine square theta, but that can obviously be exchanged for a 1, making this whole thing just dr the quantity squared. Huh. Nice, huh? Here notice I have a 2r sine theta cosine r d theta, and I have a negative, same thing over here. Positive and negative, that would give me 0, so that's gone. And here I have an r square and a sine square and a cosine square and a d theta. They both have d theta squares and r squares, but one of them has a cosine square and a sine square. So everything else could be factored out, leaving a cosine square and a sine square. Of course, that would give you just 1. So that would give you r squared times d theta, the quantity squared. Nice, huh? So going back to our original configuration here, original formula, this would give us, let's go back to green. This would give us that ds is equal to the square root of dy squared plus dx squared, but that's all that, so it would be dr squared plus r squared d theta square. It's not bad, at least I've got it from x's and y's to r's and thetas. But we've got more work to do here, because even if I tried now to add them up, let's try again using the fundamental theorem of calculus. It's great power and grace. I'm stuck here. I don't know which differential I should use, the dx's or the d thetas. You've got to substitute one out of there. Either get rid of the dr's or get rid of the d thetas. So why don't we go back to our formula here, r, that tells us the connection between r and thetas, and from there we should get a dictionary for the differentials. So we'll do that right here. dr is equal to, the derivative of 3 is 0, that would be 7, negative 7 sine of theta d theta. So a dr can be exchanged for that. So therefore this becomes the integral of my dr squared, so that would be negative 7 sine theta d theta squared plus r squared, that would be 3 plus 7 cosine theta squared times d theta squared. All that has a square root. I could factor out the d theta squared, so that would be, I should be getting paid extra for this, man. That would be 49 sine squared theta plus whatever, 9 plus 21 times 2, 42 cosine theta plus 49 cosine squared theta, and the d theta comes outside here. And all that is going from, where's it going? Oh, my limits. Oh, I said, we're only doing half of it, so we had calculated that was from 0 to 2.0 radians. Alright, I can clean it up some more here. You've got a 49 sine square theta and a 49 cosine square theta. You could factor out a 49 out of both of these. And if you did factor out a 49, that would leave a sine square and a cosine square, making it obviously equal to just 49. So I have 49 plus 9 plus 42 times cosine theta times d theta. I can even clean it up some more. That would be 0 to 2. That would be 50. 8 plus 42 times cosine theta d theta. A very doable, not exactly trivial, but a very doable integral. And a lot of times the integrals here become incredibly difficult. That's why you see this type of problem a lot. Find the integral setup only. A lot of times they know that what you get is some crazy integral. Or sometimes they'll say estimate it, whatever. Anyways, this is how you do it, just by using common sense. I know a lot of books out there and a lot of websites will just give you the formulas. Say have you memorize the formulas, but we're trying to see a little bit of why or where the formulas come from. Some rhyme and reason to this madness. Actually nice stuff here. You can compute everything. I think we should call that a day. What do you guys think? Alright. It's been fun. We'll see you guys here next time. Bye.